Right, hello. So yeah, as was said, I'm going to be talking about AFL, or rabbits for fun and profit. So who am I? My name's Hugh. I run a consultancy in Wellington, New Zealand called All Things, and so that's where I come from. And this is the slide that some people should take a photo of for no apparent reason. So what is this talk really about? So here is a lovely picture of a rabbit. I'm going to talk about rabbits. I'm not actually, but we'll get to that. So what is fuzzing? So fuzzing is sort of the art of applying random input in hopes of finding something that causes something bad to happen. So unexpected behaviors could mean different things depending on the context. So security professionals use this technique to find a whole bunch of different stuff that you might not find with just manual testing. So you can fuzz on the web. So here's a little slide on just fuzzing in the web. So in web applications, you can fuzz a whole bunch of stuff like cross-site scripting, cross-site request forgery, XXE, SQL injection. So there's a bunch of tools that will do this for you. So there's like W3AF, Burp, SAP, Wapiti. Some of them open source, some of them not. What I'm more interested in is fuzzing binaries or all the low-level stuff. So Justin gave a talk before about sort of memory errors, and that's sort of what I'm trying to find in my bounties that I do. So here, fuzzing is the attempt to find an input that will cause a crash in the binary application or the library, which could lead into some more dangerous stuff like code execution or whatever. But I mean, that's my goal, find some remote codecs. That's good. So some fuzzers that will do this. So we've got ZZUF, which is what you might call a dumb fuzzer. It basically just sends random input. There's Hong Fuzz, which attaches to an existing running program and kind of a bit smarter than ZZUF. That's also made at Google where AFL was made. So AFL is made by Lacam Tuff is his handle, and made in Google to do fuzzing on a larger scale. So what does this talk actually have to do with rabbits? Because I can see all of you are rabbit enthusiasts. You've come to the room to hear me talk about rabbits, and so far I haven't. So here is where I start talking about rabbits. American Fuzzy Lop is a breed of rabbit which is similar in appearance to the Holland Lop. However, the American Fuzzy Lop is a wool breed with wool similar to the Angora breed. And that's about where my knowledge on rabbits ended. So American Fuzzy Lop is also a tool made out of Google, which is a security fuzzer, commonly called just AFL, which is a lot easier to say than American Fuzzy Lop. The rabbit I had before, that is actually a picture of an American Fuzzy Lop. Cool. So a bit of background on me and why I'm standing up here and talking about this. So I've done a lot of research into bug bounties, used to do a lot of web application stuff, but recently, well, not so recently anymore. In the last year or so, I've started doing more low-level binary stuff. So this is where fuzzing comes in, and the binary fuzzing is quite an interesting thing to me. So I've used a whole bunch, and I like AFL probably the best because it does things quite differently. So AFL is different from binary fuzzers in the fact that most binary fuzzers traditionally take like a deterministic, very dumb approach, just send random input and no real thought into what that input is. So, as I've said here, that's kind of akin to if you grab a room full of monkeys and some typewriters, they might eventually write some Shakespeare, but it might take a long, long time. So AFL comes in and they came up with a great technique of instrumenting the code. So it assumes that you've got access to the source code, which for the bug bounties I'm doing, which is open source, I have the source code, so that's easy. So you've got the source code and you instrument the source code. So when you're compiling it, you basically work out when you're taking a branch and if you're taking a branch, you take a note, and then when you send input, you can work out the program path that input has done. So when you find another random input, you can determine whether it is taking a different program path through the application, and you can use that to tune what you're fuzzing next. So how does that all work? Basically, we compile the source code, and yeah, I just said all that, oh well. But there's also another mode, so if you don't have the source code, which for some applications you might not, you can use a binary emulation. So it basically uses QEMU emulation of whatever application you're running, and you can do similar things. So basically, you work out when a branch point is taken. That approach is like a lot slower, like an order of magnitude slower, so I haven't done that. I just stick with the open source stuff, and it still pays. So some features of AFL. There's the binary instrumentation that I've talked about earlier. There's the dictionary-based attack. There's address sanitizer, which isn't strictly AFL specific, but it's something that is very useful to run alongside AFL. AFL can also, once you get a crashing input, you can minimize it. So like instead of having a large, unwieldy, random thing, you can minimize it into something that's very useful to send up to upstream maintainers to say, hey, here's a bug. This is the smallest possible thing that I've found that will reproduce this crash. And it's also got this cool mode called Peruvian Rabbit. You give it a crashing input and it will find more crashes. So I'll just go into more detail on each of them. So the binary instrumentation, so this is just the default mode of AFL. You can force it to do a more dumb approach akin to ZZUF, but the reason why I'm using AFL is to use this awesome binary instrumentation. So to use it, you basically you have a wrapper script that AFL has a wrapper script around GCC or G++, and you recompile the binary, and it puts in all the instrumentation logic. So that actually allows AFL to, say you're fuzzing a JPEG library, and for the example here, you can start with just a string hello, and then after several 100,000 iterations, however long it takes, you actually start to find that you're producing valid JPEG images because of the instrumentation approach. It's working out that the text hello doesn't really do much, but if you change it to have the JPEG header at the start, it's taking a different code path. So hey, let's go down that track. And the blog down there shows how he produced like a whole bunch of valid JPEGs and found some crashing ones as well. So yeah, the point is you're basically getting different program flows through your program, and some of them might cause crashes, some of them might not, but to get to the ones that do cause crashes, you need to go through the ones that don't. So the dictionary feature of AFL, it basically allows you to, so like programs don't always have binary level syntax. Well, they're not just all like random binary data. So like you might have certain keywords or certain binary strings that might come up from time to time. So the dictionary feature is a tool, well, not a tool, like it's a feature that allows you to say, hey, in this file or in this program that I'm trying to run, I would expect the input to have this string or this string or this string, and a whole bunch of just like words that thing might have. So the example here shows that in SQLite you would have valid SQL commands. So a SQL command might have the word select in it, or it might have insert, or it might have update. So you can build a dictionary with all those valid keywords in SQL, pass them into AFL, and then you can just give it a simple starting case, and then when it fuzzes, it's like, hey, let's try throw in that word, or this word, or that word. And then you start finding bugs. So that's a pretty cool one. Address Sanitizer, or ASAN, is originally part of the Clang compiler suite, but then ported into GCC as well. So, in Justin's talk earlier, if you were here for it, when you overwrite the stack, nothing actually happens unless you overwrite the bit that's the return pointer, and then it's like, oh, I can't execute AAA, so that's when it crashes. But with ASAN enabled, if you overwrite the buffer by a single byte, or like a couple of bytes, I think I might actually do it with just one byte, it then crashes at that point because it's like, it knows what memory should be allocated and what's in range and what's out of range. And so with ASAN enabled, you get all these crashes that wouldn't normally be crashes with ASAN disabled, but it does show you memory corruption happening. So you can use that tool to basically find memory overflows or underflows or overreads or whatever you want, some memory corruption that you can then take to a program that isn't compiled with ASAN and potentially find similar things. So this was actually used by Han Bork. Hopefully I'm pronouncing that right. My German's not too good. So he used this ASAN to find Heartbleed. He didn't find Heartbleed originally, so after Heartbleed came out, he's like, I wonder if AFL could have found something like this. So he got OpenSSL, a vulnerable version, and he compiled that with AFL, and then he wrote a simple C test program that basically took a handshake, starting the first handshake, and then went through the 4 TSL handshakes, and then compiled that and linked it with the OpenSSL that he compiled with AFL. And found that after half an hour, he found the Heartbleed bug. So, I mean, it's a bit of a moot point because he knew where he was looking, but it does show that this sort of approach could potentially find issues similar. So the test minimalization, I find this useful because when you're generating inputs, they tend to get a bit longer and longer, sometimes shorter, sometimes longer. But the input that you get looks kind of random. By definition, it is just random input, just happens to crash the program. But when you're filing upstream bugs, and you say, hey, I found this input, it looks like this, and you give them like a 200 byte string, and it's just full of random characters, hey, this crashes your program. It's much better if you can run it through AFL tmin, which then makes it a lot smaller, so you might be in the order of like 50 bytes. So this makes the maintainers a lot happier, and it also makes my job of triaging and finding where the bug is a lot easier sometimes. The last feature I was going to talk about before walking into some of the bugs that I've found is the crash exploration mode, or Peruvian rabbit. So normally when you run AFL, you give it a input that doesn't crash the program, and you're trying to find an input that does crash the program. So the Peruvian rabbit mode, you give it the input that does crash the program, and then it goes through and finds more crashing inputs that take different program paths while still crashing. So this potentially, maybe not, I haven't read anyone that's actually done it, but this potentially could be used to automatically find exploits. I myself find it easier just to go and find the exploits manually after one crash. But it's got potential. So those are the features that I wanted to talk about. And for the rest of the talk, I'll just be talking about specific bugs that trigger some of the different features. First off, this is basically how easy it is to run AFL files. So you basically set your compiler to AFL GCC, you configure make. So these are C applications, or you can do C++ as well, or anything that's supported by Clang. And there's also forks for other languages as well, but I've just done the C applications. So you compile it, you make an input directory, and you make an initial seed. So this should be like a sort of valid input to the program, but it could just be completely random stuff. And then you just run AFL fuzz, pass it the input directory where all your initial seeds are, and you pass an output directory where it's gonna store all the fuzz stuff it's creating and any crashes. And then right at the end you say this is how you run the program. So on the right hand side you've got a @ sign. So that is basically, that's going to be replaced by the file that contains the fuzz data. If you don't include the @ it's just piped through standard input. So yeah, you can do either way, and different projects rely on different things. Once you run it, it kind of looks like this, and that looks really blurry, I don't know. But so what we've got is, up here, this is the results, and after you get a crash, this number will go up to 1 or more, and also turn red. So anything that's red shows something that you should probably look at. Cycle's done, so after it goes through and does a couple of cycles, they will change to different colors. It's got a whole bunch of information that's kind of technical, but once you get to know how it's working, it is useful. And then it's got some timing results up the top, so how long you've been running it, when was the last time you had a crash, when was the last time you found a new unique path. So I mean, it's a reasonably simple interface. You run it, and then you just leave it forever and come back. So I mean, sometimes I'm leaving stuff for a couple of weeks, sometimes I leave it for a couple of days, and sometimes I leave it just for a couple of hours. It's basically until I find a crash, and then I will start triaging that. So bugs I've found. So these bugs I've found based on, there have been bug bounties that pay money for finding bugs in a whole bunch of projects. These are 3 that I've found bugs in, so I thought I'd talk about them. So there's PHP, programming language, libxml, so that's a low-level library to parse and do XML stuff. And then we got giflib, which is used low-level library to do GIF rendering and other stuff with GIFs. And I've also found some stuff that haven't been released upstream yet, so I sadly can't talk about them. But hey, that did do that. Need to do... that one, sorry. So these are some bugs I found in PHP. So PHP is a programming language. Everyone says it's really insecure, but hey, like, there's a lot of PHP developers, and there's a bug bounty for it. So I come along and I fuzz with AFL and I find a whole bunch of stuff. And I got paid for it, so that's good. So as you can see, there's a couple of memory issues. So the memory out of bounds write, so basically I'm writing to memory that wasn't allocated to me. Got a couple of just not so great null pointer dereferences, so like I've overridden something so it's just null, then it dereferences it, and then it crashes. Not so exciting. And then we got a buffer overread, which is basically what the Heartbleed bug was. It read data out of memory that wasn't allocated. So I'll just go through all of these, and then I'll go through the other bugs in the other programs. So the first one, we had a memory out of bounds write. So we were writing stuff that wasn't allocated to us. So this was affecting the core language syntax of PHP 7, which at the time was in beta, but now is not beta. So to find this, I use the dictionary approach. So to do the dictionary, I basically scraped php.net, which is the documentation site, and I got all the keywords of core PHP, put them in a file, say, hey, these are the keywords that you should expect. So that was reasonably simple to do, and ran that. Can't remember how long it took before I found anything. Problem was, this bug actually required PHP to be compiled with optimization set to fillers, and it wasn't reproducible on the current stable version, which was 5.6. But hey, it's still a bug, so I still reported it. So the test case got minimized to so those of you that don't know PHP, that's just a opening tag to say it's a PHP file. That $A is a variable. We're accessing something, we're appending something to the array, we're divide equaling whatever that is, and sending it to $A, which is potentially an array, but at the moment it's nothing, and then we're sending it to A, which is just a constant string because it's not wrapped around anything. It also worked for divide equals, times equals, anything with an operator before the equals. This program isn't actually strictly valid because $A isn't actually defined beforehand, but PHP, who cares? So I found this bug and I traced it back to Zend fetch dimension address rewrite in the source code. PHP source code is very beautiful. Everyone should look at it. Secretly not. But once I found the bug, I made a patch, and out of interest, I used git bisect to find the commit that actually caused it. And I found that it happened to be fixing a similar bug, which was another security bug filed earlier by someone else, and a patch was made, and then that introduced my patch, which is why it wasn't in the stable version, just the beta. So, hey, that was fixed all upstream, and yay. So, on to the next bug. So at this point, the PHP team decided that any bug in PHP 7, which was then in beta, wasn't actually really security issues because, hey, no one uses it. You know, I'm like, oh, lame. Okay, so I changed my fuzzing focus to focus on the 5.6, then current 5.6.12, which was the then stable version. So I used the same technique, fuzzed over the language features, and got them from php.net, built a dictionary. So yeah, when I did PHP 7, I didn't have function names. I just had the plus minus, all the operators, and yeah, basically all the operators and no function names. So this one I started doing function names as well. And then I stumbled upon this gem. So here we've got a function ob start. So this is when the output buffer is starting, it calls this function. So basically, when you start writing anything to the page, it's going to call that function. And there's a 1 right at the end there. That 1 was required due to weirdness. In the bug report, it's got a lot more. But basically, if there was a file that was just named 9, no extension, and it had a PHP class in it that had no name, then you don't need the 1. So, yeah, or you need the 1 if there is a 1. You just don't want to know why. I'll tell you why. So the problem with this bug, it was chaining together the userland function of what was it called? Userland function of ob start with the C-level function of SPL autoload. So for those that don't know PHP, which is probably most people, SPL autoload is a function that you normally call with arguments that will look for directories to load class files when you don't actually include them in your project. But yeah, so the problem is that you're using a userland class function, and you are then calling the C-level stuff, so PHP function calling the C-level stuff, and the C function is expecting parameters, but you're not passing parameters, so hey, let's see, it just makes up random parameters. And it was a bit of a nightmare debugging, but I found it. So it happens when, SPO autoload is looking for something valid, but random parameters are sent in because it's sending to a C function. C function couldn't find anything, so it just got random stuff off the stack. And that's where the whole file named 9, because the second random argument wasn't actually as random. Oh no, the first argument wasn't random, but the second and further on were random. And so 9 just came out of it. And so if it couldn't find a valid PHP file, it would throw an exception, and it would use a little macro called active op line, which is the active line that your operation is running in C, so it could give you a nice stack trace. Problem is, that wasn't set because it was being called in a weird, unusual way. So I made a patch and I sent it in, and it got applied. PHP then decided that any just core language features, they don't really treat as security either. Because, hey, you've got code, you can just run the system. And so, yeah, that makes sense. I changed the fuzzing target once again. So now I'm fuzzing core modules in PHP. So I made a couple and I ran AFL over it, and I found some bugs. So one I found is in the EXIF module, which is doing image format tags. So I made a wrapper PHP script, which is that. I'll bump that up again. So it's just a simple PHP script, EXIF read data, and take the first parameter from the command line. So I can just run AFL on that PHP file and then pass the file name. So this made use of ASAN, that memory technique that I mentioned earlier. So this read like a couple of extra bytes, and ASAN just gave it up and was like, nah, you're reading bytes that weren't allocated. So it then segfolded, which meant AFL could catch the crash, but it wouldn't normally catch a crash if ASAN wasn't in. So the file I found was a TIFF file, so an image format from the 80s or wherever. And so if I had a tag of make or model or company that was exactly 32 bytes long, it was copied into a place, and the buffer expected 32 bytes, but then C needs that null on the end, and the null wasn't there, so it just kept on reading. So I made a few patches, talked with the upstream maintainers, worked out which they wanted, and then that got applied. So what profit did I make from this? So this bug bounty was through the Internet Bug Bounty program. So it's a whole bunch of big companies that pull in money, and they give money for popular programming languages, OpenSSL, Apache, Nginx, a whole bunch of projects, and they pay money for finding bugs like this. So I was told expected turnaround was a couple of months. It ended up taking about 5. But I ended up getting paid $3.5K for just those 4 bugs, which I was happy with because I was only working like 1 day a week, and I found that all in 1 day, I think. So that's a good bit of work. So yeah, work was not much. There's more to come in the pipeline that eventually they'll... So I have to file it to PHP. PHP decide that it's a bug, they fix it, they patch it upstream, then I talk to Internet Bug Bounty, and then they pay me. So it's kind of a roundabout thing, and it takes a while, but I've got some more in the works. So next I'll talk about libxml. So this is a low-level XML parser library, and I found some buffer overreads in the XML parser, and it's also got an HTML mode, and so I found that. These both required ASAN, so they didn't crash normally without ASAN. So yeah, might not be as good, but yeah, the first one was a test case where the entity had an extra character after it, so it's an unterminated entity, and it's meant to fail. So it sets its internal state to end a file, and then just doesn't check that. So not sure why they said it. So I made a... Oh, that one. Yeah, so I made a patch to actually checked the return result, and that got applied. So that's good. The HTML version, so that's a empty tag, so that bracket, and it needs a 0 to have some output. So that tries to read past the end of the input and returns random memory. So I made a patch to fix that. All it did was check the length of the tag, because it was hard-coded to start at 1 for some reason, which just doesn't exist if it's an empty string. So the libxml was managed by a Google application security vulnerability reward program, and they replied like within the week. So hey, a lot quicker than the Internet Bug Bounty, and they gave me $500 for both those bugs. So GIFlib is a very old library. It's actually still hosted on SourceForge, if people actually remember SourceForge. It's a library that is used to display cute bunny rabbits and babies with cookies getting stolen, and a whole bunch of kittens, and I decided to get a, I don't know, he looks really sad after, and they're like just really confused, like what just happened? I wanted that cookie. I don't normally have gifts in, but I'm talking about gifts, so hey. So GIFlib, I found some bugs in GIFlib. They're public, so they're upstream in GIFlib. They've been patched, they've been released. I just haven't been paid yet, so this is through Google as well. Secretly I have been paid, but I won't put it in the slides just yet, because I haven't updated the slides, but I might talk about it. So I found some boring null pointer dereferences, I found some buffer overwrites, and a double free exception. And I don't have anything on them because I haven't updated the slides, because now they're paid. But yeah, so the total profit of all the fuzzing I've done, so I work like 1 day a week on just fuzzing, and so far this is definitely paying for that 1 day a week. Other people's mileage may vary, so hey, and it is now time for some questions.